So, if I keep getting used to the Italian living here in Pisa, I'm going to forget to start speaking Romanian. But we were discussing before you came in about the heat right now in Pisa. So I was trying to explain to Stefano that it is a superposition, natural variability, the seasonal cycle, and anthropogenic forcing. Okay? So that's really what you're trying, by the end of these lectures, you should have a better understanding how these things, work out in reality and how to model them mathematically. Okay, so you don't want to go to full style. You have to split the screen, because I think yesterday we had the full.
Yesterday it was different. Now I'm trying to
okay.
adapt to the new.
Okay.
Because this is streamed from inside the software that is managing the meeting. In the other case, I was doing from my computer. But this should be better because
okay.
Okay.
Okay. So today, oops. I'm trying. So let's see. There's a pointer. Pointer. Okay.
You can
start. So notice that for each lecture I start with essentially with the same slide, except that I try to emphasize what out of the overall title we're going to be talking about in the particular lecture. So today in the morning, it's atmospheric low frequency variability and the things that go with that. But now we're going to have to wait for Stefano to change the slide because I cannot do so. So,
okay, they will bring us. They have to open the.
In the meantime, please move to the next slide. Okay, so there's some great things about these hybrid talks that we got used to during the pandemic, but because people from far away can watch, but it's also a pain in the behind, as we say in the US, to try to manipulate all the information technology, IT. So, okay, atmospheric low frequency variability. So you see at the bottom, there are all these acronyms which are being spelled out. Since these days we do more and more collective research, you will notice that as soon as there are 2 or 3 people working on the same topic, there's an acronym. And as soon as there are 1 or more tenth of people, there are second order acronyms, acronyms of acronyms, extreme. So anyhow, low frequency variability and long range forecasting. So I told you that in the same way in which a lot of what we learned about deterministic chaos has to do by the work of Ed Lorenz, that I mentioned in greater detail. Okay, so a lot of what we know today about deterministic chaos and predictability and so on has to do with the development of numerical weather prediction. Here, to a large extent, the motivation of the studies of low frequency variability is the attempt to carry out long range forecasting, in other words, beyond the horizon of detailed prediction, which essentially is, which is largely due, as we said on Monday, to the exponential divergence of trajectories, but also to other processes such as energy cascades across the wave spectrum. So, next one, please. So this was what we talked about on Monday. Scale dependence of atmospheric oceanic flows, the effects of turbulence on predictability, basic facts of large-scale atmospheric life. So this was really the meat of the lecture on Monday, and then going into flow regimes, bifurcations, and symmetry breaking, which we will have more to say about again. Okay, next one, please. So, observations of persistent anomalies, blocked and zonal flows, characteristics of persistent anomalies, the deterministic chaos paradigm, force dissipative systems, successive bifurcations, predictability and prediction, and then more about what I call waves versus particles. This is really just a very vague analogy. You know, of course, about the duality within quantum mechanics, two representations of what happens at subatomic scales. But here we're not talking about subatomic scales. You're going to see what I mean by this. We're going to, the particles are going to be the multiple regimes, and the dynamics then is the Markov chains between these multiple regimes, and the waves are going to be oscillatory modes, and the broad spectral speeds that I talked about on Monday. Which one is it, and how does that help? Next one, please. Okay, observations of persistent anomalies. How many of you have heard about blocking? I don't know whether you get, given the fact that there isn't really a national weather service in Italy, I don't know how much, you know, Italian media talk about weather phenomena. So have you heard about blocking? Some people have. Okay, good. So, you know, during the break, because unfortunately the other ones where they should tune in to hear about that sort of thing. Okay, next one, please. Okay, so this is out of a paper which was published, I mentioned, at the Journal of Atmospheric Sciences, you know, a couple of decades ago, was a sort of flagship journal, the leading journal of the American Meteorological Society. I think I also mentioned already Masaki Moto, now was my first PhD student at UCLA, and is now a full professor at the University of Tokyo. And this was essentially out of his PhD thesis, but published in the first one of two papers that appeared in 1993, so this is well, 30 years ago. So what is limited contour analysis? Well, what you're seeing here, remember what I told you on Monday about the fact that if you do sort of a map of the 500 millibar surface in the atmosphere. So, you know, the pressure at the surface is 1,000 millibars or hectopascals. They are identical in size, they're just two different words that are same thing. It used to be millibars, which I was to see on those old thermometers, and now it's more systematically within the so-called international convention of units called hectopascal. So it's 1,000 at the ground on average, and so 500 is sort of the middle of the atmosphere. Half the mass is below, half the mass is above. And it happens to be a good surface to look at because at that point, large-scale motions truly, to a very large extent, horizontal and non-divergent. Okay? So basically, if you do the topography of the surface and the way that, you know, if anybody goes hiking or mountaineering, you know what a relief map is. If you do the relief map of the surface, the contour lines, okay, are to a very good approximation streamlines. Okay, so as you look at these maps, okay, what you see is essentially contour lines of flow at the middle of the atmosphere. Now, what is meant by limited contour analysis? This is a certain professor at MIT, Fred Sanders, who came up with this stuff. What you're seeing here is not a photography of this surface on a given day, but it is just a particular contour which sits pretty much at the core of the jet axis. Okay? So basically, you have to think of these as being the place where the flow is fastest at this altitude. So you're seeing a stereographic map, looking essentially over the pole, flattening things out. And it's this particular contour every 10 days. So you see that there are times when the contours really fall on top of each other, here for instance. So this is, I hope you're here, these maps are done differently depending on whether you do your meteorology in North America or in Europe. Okay? In North America, typically they are oriented in such a way that you see here Florida. Okay? And Europe, we are over here. Okay? So this, for instance, is a very large obstruction of the zonal flow. Remember what I told you about the mid-latitude westerlies, okay? So basically the flow goes like this in general, and when it is very close to a line to a constant latitude, okay, it is called zonal. That's the word for it. And so, very much of the time, it is not very far from zone. Here, for instance, you have a very large bump on these streamlines, okay? And that's a block. And when you have such a block, instead of, let's say, the flow in Pisa, coming from the west, okay, and bringing marine air, it comes from the north, or sometimes even from the northeast. So in winter, it gets very cold. Okay? And in summer, when you have such a block, it gets very dry. Okay? So you have a drought like you've had now in Italy for I don't know how many months. Okay? That's when this block persists. So, what we're looking at here are such contour maps for 10-day episodes. I'm trying to remember, yes, they go like this because you see, in East Asia, you used to write from top to bottom, not from left to right, okay, as we do north of the Mediterranean, nor from the right to the left, as we do to the south of the Mediterranean, but from the top to the bottom, okay? Actually, traditionally, it went from the top to the bottom and then from right to left, but now many books are printed, so these figures, you have to look at that, Massa sort of made a compromise, it goes from the top to the bottom, and then again, from the left to the right. So this is what happened during 10 days, so you see that basically, there was a large fraction of the flow, which was pretty zonal across, the Pacific. And there was just a little bit of deviation between these lines from one day to the next, here and then here. So this is fairly agitated flow. This is very persistent. So when we talk about persistent anomalies, is that instead of just having these large waves coming through that bring weather with them, you have an obstruction like that. Okay? So that's essentially blocked and zonal flow. Next one, please. This is, one semester of dynamic meteorology for people who only want to learn dynamic meteorology. So I try to do this as fast as I possibly can. Okay. So this actually comes from a paper which was a collaboration between the group of Harry Sweeney, who was one of the leaders in establishing that deterministic chaos doesn't only happen in small oscillators, things that can be modeled by 2 or 3 coupled ordinary differential equations, but in real fluids. He did experiments while he was still at City College of New York on such things. And so at the time, he had moved to the University of Texas at Austin, and I had moved from the New York University Underground Institute to UCLA. And Eric Weeks was a PhD student of his, and Jerry Urbach, a PhD postdoc, and Yuval Tian was my student, and Kaya Reader, my postdoc, and this appeared in Science, reporting the results of an experiment in a rotating annulus, like I showed you on Monday, but where the flow was not driven by differential heating, between those two reservoirs, but by barotropic pumping. There are holes in the bottom of the annulus, and the flow got pumped up near the outer border and sucked in near the inner. So this did away with clinical instability, which got in the way, and really allowed us to look at this problem of blocked versus zonal flow. And these pictures are just the motivation of the papers. These are exactly the kinds of things that you saw on the previous slide. This is essentially zonal flow that persisted between the 13th and the 22nd of December of 1978. Happens to be, a year when it was very nicely zonal all around, okay? And this is blocked for a decade, 10 days in January of 63. That was a very famous blocking event in which, much of the Midwest of the United States, you see the flow came from the Northwest. So it got very cold in Ohio for quite a while. Actually, this lasted for a full month. Okay? So that's what we're trying to explain, the difference between two atmospheric situations like this. Next one. Okay, characteristics of persistent anomalies. So let's see, next one. Okay, so essentially there are these features, geographically fixed appearance and regional capital. Don't mind the little footnotes because that goes too far from the time we have today. So geographically fixed appearance. So those blocks, if you can go back to the map, please, 2 slides ago. Okay, so you see that these blocks always happen, these are so-called West Coast blocks. They always happens just off the coast of North America. And as I'll tell you afterwards, that's because you have the Rockies here and they block the flow. And then when there is blocking, so this is sometimes called the Pacific North American sector, and this is called the North Atlantic Eurasian sector. The blocks here are, again, off the coast of Europe, west coast of Europe, but here, the only topography that you have is the Alps, which are not north, south, east, west. So this is not as well understood as this. Incidentally, there are also deep shaded differences in the details. This is just a so-called ridge, and this is a so-called omega block. You see that it's a omega, capital omega here. There's a high and the low below. And it's less well understood, but it might have, sometimes one refers to the usual topography as mechanic topography and to the other one as thermal topography. The land-sea contrast, temperature difference between the two, and the fact that in the same way that mountains tend to lift the flow, hot air will move up and create the region in a different way. Okay, so let's go back and go forward here. Okay, so there's a geographically fixed appearance. So the lower boundary condition plays a role. The Earth, sometimes one talks about an aquaplanet in which such things do not exist, in which the surface would be perfectly smooth. Then persistence, that's why they're called persistent anomalies. These are references for people who have documented the persistence of these features. Recurrence. So you know, these things happen again and again at irregular intervals, but again and again in the same places and last for long. So there's regional character persistence recurrence. So recurrence reminds you in dynamical systems of things like Poincaré recurrence, and you know, things will come back to the same place or close to the same place, but one doesn't quite know where. So just to give you an idea, such blocking events happen typically. A lot of the studies were done on Northern Hemisphere winter. So first of all, more studies were done on the Northern Hemisphere than in the Southern Hemisphere, because there are more people who do the science who live in the Northern Hemisphere. And then it is done during winter because the flow is more intense, and it's sort of what happens is more striking. Although, of course, summer droughts are very important. So, in a typical winter, so let's say instead of exact 3 months, talks of December, January, February, DJF, it's instead of 90 days, one talks about 100 days, let's say. So in 100 days, typically you'll have a blocking event 2 or 3 times, but you know, without further specification. And then finally, and very importantly, barotropic structure. So I told you that in meteorology, barotropic just means that essentially things do not change in the vertical, okay? And one talks about barotropic or third adjustment, see next page. So basically, one doesn't exactly understand why this happens, but as opposed to baroclitic instability about which I told you on Monday, it's truly three-dimensional, and there's a certain tilt with height of the features, the troughs and the ridges. This is sort of straight up and down. Next one. So, you know, just some of the explanations of why this happens. Statistical theory of turbulence. So, you know, we encounter Joe Charney's name again and again. You know, most people outside meteorology think that the greatest meteorologist of that generation was Eddie Lorenz, because his work was much better known outside meteorology. But actually, it was Joe Charney. And, you know, name will show up again, but he has a very famous paper called Quasi-Geostrophic Turbulence, which says that it is essentially two-dimensional. I mentioned this on Monday. Evolution of Gauss-Lindbergh eddies and wave makers. So, you know, as these middle altitude storms develop, they sort of, as they weaken, they can straighten up also. And there's a third theory that I won't go into. So this is just to tell you that the extent of our ignorance, you know, why I get very irritated by the statements that science has been done and all that remains is to adapt and mitigate. It is true that we should adapt and mitigate, but we should also keep trying to learn what's happening. Okay, next one, please. Okay, so I mentioned this already a couple of times, the deterministic chaos paradigm, force dissipative systems first, please, next one. Okay, so here are actually some equations. Most fluid dynamical problems and many other problems in biology, chemistry, and physics lead to ordinary differential equations or equivalent partial differential equations, which are roughly speaking this form, so I'm just using the dot for the derivative with respect to time. So the finite number, capital N of variables, and each one, the right-hand side looks like this. There's a quadratic term, there's a linear term, and there's a constant term. So the quadratic terms in this equation represent a nonlinear advection, you know, u dot del u. So again, mentioned the fact that there's a little bit of a different terminology. In general fluid dynamics, one speaks about convection independently of scale and of vertical or horizontal motion. In dynamic meteorology, convection is essentially what happens in clouds. It's something that happens in the vertical direction. Okay? And what happens in the horizontal direction is called advection. Stuff is carried by the large-scale horizontal winds. So this term is associated with the Jacobian and the quasi-catastrophic equations, which I showed you on Monday. And again, you can find all this stuff on the web, on the. So the above equation is autonomous. In other words, the A's, B's, and C's do not depend on time. This is immensely important, and the huge theory of dynamical systems until fairly recently was based on this assumption, because one of the very simple things it does is that two trajectories cannot intersect. If you are at a certain point, the direction in which you would go in phase space is uniquely determined. That will no longer be so if you let any of these terms depend on time. Okay? So it has unique solutions for all initial data. So in particular, that means that the trajectories cannot intersect. And these solutions depend continuously on the initial data. When the solutions exist for all times, which is not guaranteed, then these equations define a differentiable dynamical system, or DDS in particular. We shall assume that the system is forced. In other words, the C's are not all zero, and dissipative. So I don't know how many of you were yesterday at the Cantarino di Giorgi at Canaldo Liberano's talk. That was about hyperbolic, non-Hamiltonian, non-dissipative systems. It's a huge area in mathematics, and it's largely motivated, of course, by celestial mechanics. It turns out that even in celestial mechanics, it is not true that the motion of the planetary system is Hamiltonian. There are very small dissipative forces, okay? But I don't have the time to go into that. So the dissipation is enormously important, and essentially, within the world of observed reality, Hamiltonian is vanishingly small. Everything is dissipative. If there were enforcing, it will come to S. So the quadratic terms are necessarily energy conserving if you have this anti-symmetry property. And so the orbits of this describe a flow in the phase space. Now, why do I say that it is not, solutions do not exist for all time? So, people who haven't done serious mathematics in the United States can say everything worth knowing I learned in kindergarten. For researchers, kindergarten is graduate school, or what you call it in Europe, postgraduate school, okay? So for people who have not done serious mathematics in kindergarten, okay, statements like that look a little bit annoying, but they are important because something as simple as x dot is equal to x squared, solutions are unique and depend continuously on x naught, but they blow up at t equals 1. Okay? And for instance, it is not clear to this day that the solutions of the Navier-Stokes equations in 3 dimensions do not blow up at some point, although it's not clear what would happen to all the fluids in the world if they did blow up in physics and not just in mathematics, but that probably just means that the model is not very good. Okay, so, this is another full course in differentiable dynamical systems that I'm trying to give in one slide. Next one, please. Okay, successive bifurcation. So you have such an autonomous system with the properties as I described. What happens to the solutions as you change parameters? Next one, please. Okay, so I'm reminding you now of the slide that I showed you on Monday about this apparatus, the differentially heated rotating annulus. And next one, please. So this is called a regime diagram in which we show the properties of the solutions and the functions as a function of 2 parameters. And again, this experiment has 15 parameters, but these are the 2 which are the most important ones. Okay, and we will try now to explain the changes between the Hadley regime or Ospie regime vacillation, and eventually presence of next one, please. Okay, this I didn't show you on Monday, but it's important. So this experimental for fixed apparatus height, D, and width, the gap between the two reservoirs of warm liquid and cold liquid. So gap with L. Fluid expansion coefficient alpha, viscosity mu, one can change the rotation rate omega, I told you that's the easiest thing to change, and the temperature difference between the two reservoirs. So, you know, the mechanic one is you just basically have a tuner for your home. Out it under the table, and then, well, changing the temperature of the fluid takes a little bit longer, but it's also relatively easy. So, as well, this is now, I told you this on Monday, but let's go back one slide, please. Okay, so again, you know, these, I told you that these straight lines are like that because omega enters both on the abscissa and on the coordinate. Okay, so we are calling this now the high numbers, that's what it should be called. Although more common is from the thermal number, so you move up and down, and when you change the difference in temperature, you move up in this direction. Okay? One forward. Okay, so we're going to associate these transitions with bifurcation. So this is just an example of amplitude vacillation. You see here that the amplitude of the wave is pretty small and the width here is much larger. And in this case, you have so-called tilted trough vacillation. You see that the troughs of the waves here, troughs of ridges, are essentially in a radial direction. Here they're obviously slanted with respect to the radial direction. And the next one. Okay, so in that same year, well, you know, Ed Lorenz was not quite Albert Einstein, but, you know, the honors we had was 1905, in which Einstein wrote 3 papers, each of which launched 1,000 ships, or tens of thousands, hundreds of thousands of papers. Ed Lorenz actually also managed to write 2 papers in 1963, one of which is known by everybody outside dynamic meteorology, the one about the convection model of the butterfly. But with respect to, you know, that model is really what is sometimes called in the physical component of the dynamical systems community a metaphor. You know, it's not really a terribly good model of convection, and it certainly has very little to do with large-scale atmospheric flow. But this is actually a paper about what happens in one of these experimental devices and in the atmosphere. Okay? Actually, at that time, Ed Lorenz was not so familiar with the work of Ray Hyde. In Britain, there was another person in the United States, at Chicago, Dave Foltz, who did such experiments in a dish pan. So instead of having, you know, very nicely aligned 2 cylinders and so, there was just a dish pan in which also waves like the Rossby waves. But that experiment was harder to control and really what survived in the long run. You know, Dave Foltz was already already a full professor at the University of Chicago, and he did this. Ray Hyde was just a graduate student at U, and it is the work of Ray Hyde that is okay. So this is a model of the, let's just say, of this sort of stuff. And he was motivated by what's called the atmospheric index cycle. So there were 2 papers by the same Carl Gustav Rossby in 1939, and by one of the major figures in 20th century geophysical fluid dynamics, meteorology, etc., and found that both the Geosciences Department at the University of Chicago and later the one at MIT. And Jerry Nemiah, so actually got his degree at MIT, but was mostly an observational geologist. He was clearly inspired by the Rothe-Dinganis results, so he was modeling this in his paper. So you have two layers of fluid. So you have, this has a solid lid, okay, solid bottom, flat, and this is the interface between the two layers. So this, the overbar indicates a horizontal mean, and this sigma which enters here is a representation essentially of the stability, a non-dimensional version of essentially the density gradient between the two layers. Each layer has a constant density, and this is a non-dimensional version. So what you are seeing is the fluid, the quasi-geostrophic version of those ordinary differential equations that I showed you. Okay? So this is now the partial derivative of the Laplacian of psi. So psi is the stream function. Okay? And I'm sorry, again, in much of fluid dynamics, in particular in dynamic meteorology, instead of just using a Laplacian, operator, which is that, one uses this. Okay? Partial of the Laplacian of the stream function, essentially of the vorticity, is equal to minus the Jacobian. Usually this is written plus equals 0. But, this is equal to minus this. So this is essentially the Jacobian of the stream function with the Laplacian of the stream function. And tau is the difference between the stream functions in the upper and the lower layer. Okay? And so instead of writing the equation separately for the upper and the lower layer, it was writing here the mean stream function, the mean between the two layers, and the difference between the layers. And then there's an equation for the temperature, which looks like the Jacobian of the stream function with the temperature, and where this vertical stability parameter intervenes. And then this vertical parameter is also given an equation like that. Okay? So say here something that's called in the jargon of dynamic meteorology the thermal wind equation, which is essentially this. This is a mistake. There shouldn't be t on both sides because if a is equal to 1, one of these is tau, not t. Depending on the field. Okay, next one, please. So this is a simplified version of the regime diagram in which we see now the logarithm of the Taylor number, the logarithm of the height number, and again, omega changes slantwise like this with a constant difference between the two reservoirs, a constant temperature. This down here is a Hadley regime, so in other words, where air rises at the equator or close to the inner reservoir and goes radially outward, goes down and comes back like this. So axisymmetrically stationary. And then you have two wave regimes, one in which things are purely periodic and the other one in which they're quasi-periodic. So again, I'm using quasi-periodic in the usual mathematical acceptance. There are two angular velocities which are incommensurable, in other words, the ratio of which is an irrational number. Okay, so the two angular velocities are the one of propagation of the wave around the annulus, and the other one is the frequency of the vacillation in either amplitude or shape. Okay, and then finally down here, quasi-turbulence, which is aperiodic. So what I say here is Lorentz studied a truncated model of 14 ODEs. He essentially obtained the first few bifurcations up to and including the quasi-periodic vacillation regime. Beyond that, the low-order truncation prevents one from reaching the quasi-trophic terms. Clearly, as things become more complicated in spatial structure, so I told you that there is very often in a spatially extended system, a connection between the degree of complexity in space, number of waves you need to describe the flow, and in time. So, you can get obviously to deterministically chaotic with three equations, but you cannot have a very complicated spatial structure. So that's why essentially the Lorentz 63A, the one that everybody knows about, deterministic chaos, etc., is not a very good model of convection because it only essentially shows the transition from purely homogeneous flow between the upper and the lower plate, and everything is homogeneous in this direction, to so-called convection holes, and then from that it goes directly to something that is irregular in time but has no interest in spatial structure. Okay? Here he was able to get to something that reaches quasi-periodic, and I'm going to show you the details in the next slides. So what I say here, today such studies can be carried out on the full system of high resolution equations. Okay? So again, fully developed turbulence with cascades to very, very small scales is still difficult, but the bifurcation tree that I'm going to show you here for this system can be carried out much farther. Next one, please. Okay, so this is essentially the bifurcation tree or successive bifurcations as described in the 1963 paper of Lorentz. But this is not how he represented the results. Okay? These representations in terms of systematically of bifurcation theory, etc., are, sorry to tell you, from my 1987 book. Okay? So the numerical results are from Lorentz's work, but in 1963, that was not the way that people thought about it. So the general idea in such a tree is that as we push the system harder, it responds by coming up with a more complex response, i.e., it loses symmetry in both time and space. In time, it may go from being steady state to being periodic, quasi-periodic in between. In space, it often goes from being homogeneous to periodic, and so in other words, waves in time, in space, and then to irregular. Thus, the two kinds of symmetry loss are interrelated. So here, K is, can we go back to the system of equations, please? K is this guy. It essentially stands for the friction between the two layers of fluid. Okay? Doesn't terribly matter, but in general, when you do bifurcations, you have two kinds of parameters. The one which allows you to control, sometimes called bifurcation parameter, sometimes control parameter, depends whether a lot of case engineers tend to use more control, there are more control freaks, physicists tend to use more control, mathematicians more applications, etc. But you have one parameter that allows you to, to hurt the system more and more, and the other one which tries to soothe it more and more. Typically, in anything that has dissipation, the parameter that has to do with soothing, pouring oil over the water, is dissipation. The other one is some measure of the force. Okay? So, back to the bifurcation tree. Okay, so the general situation is if you have a partial differential equation, you typically talk about u and not x. So U sub t is partial derivative with respect to U is a nonlinear function of U, including derivatives, spatial derivatives of U, and mu a parameter, and you have some fixed point, which the right hand side is 0. So when we say for PD, the right hand side will include spatial derivatives of U and this fixed point. So now, if this in the finite dimensional ODE case matrix and in the general case linear operator, essentially the partial derivative of n with respect to U, at this fixed point is non-singular, then a unique branch of solution through it exists and is given by solving this equation to yield some approximation like this. So U approximately equal to U naught, the fixed point, plus partial derivative of U with respect to mu, which you compute by the implicit function theorem, okay, at U0, 0. The points at which the determinant, or, well, the appropriate thing in the infinite dimensional case, has just a 0 eigenvalue, i.e. those where the implicit function theorem fails and hold modification points and then in general isolated. So that is very important because it says that aside from, under suitable conditions of differentiability, smoothness, etc., okay, the bifurcation, these singular points are isolated. And in between, you can follow a branch of solutions as if things were linear by some application of the implicit function theorem, which in numerical terms is called pseudo-Ackermann continuation, more generally a continuation method. Okay? So fear not, in general, you can advance along such a branch doing your little trick, which now can be done in millions of variables. Okay? There's software developed which allows you to do this implicit function theorem trick for essentially what is called general circulation models. The kinds of models that the IPCC, the Intergovernmental Panel on Climate Change, uses in its so-called climate intercomparison sets. So, okay, near such points, the dependence of the solution is parabolic in the parameter mu. So, when you move along one of these branches, you can linearize, okay? But when you get to a point like this, for a moment you don't know where you go, and so you have a bifurcation and something else happens. So what happens here, this is the Hadley regime, homogeneous in both space and time. These are regular periodic Rossby waves, so periodic in space as well as in time. Here you encounter vacillation. Here something else happens, which is interesting, and here you get a homoclinic orbit in this low-dimensional system. Well, not so low-dimensional, it's an intermediate dimensional system of 14 OBs. And I'm going to come back to such global bifurcations later in this series of lectures. And this is what happens now really in this model, because you run out of resolution to go further than quasi-periodic to something that really looks like quasi-periodic. Okay, and then some other things happen, which this is an unsymmetric vacillation, this is a symmetric vacillation, the nomenclature of Lorentz without the diagram, and here there's some sort of turbulent behavior, not really turbulent in the sense of having lower, any sort of cascading to smaller and smaller scale in space, but regular time, and then you go back to another purely periodic regime. And again, the fact that this is an artifact of the model of the limited resolution of the model. Okay. Let's go to the next one, please. Okay, so now let's come back to the relationship between all of this stuff and what motivates it. So this is pretty amazing for you, I'm sure, because you are used to seeing, spatial plots in live color and so on. When Lorentz was doing this in 1963, there were no such things even in black and white. Okay? So what is done here is there's a printout of numbers. And then there are hand-drawn contours between the numbers which show the stream function. Okay? Now, it is very interesting that I found out only recently, and actually the world at large found out only recently. Ed Lorentz was somewhat of a loner, okay? I actually had the opportunity of knowing him in person, even hiking with him. I think I mentioned private conversation here already, the Varna summer school in 1983, where he was one of the invitees, and we went hiking on the weekend between the two weeks of the course, and I had already met him elsewhere before. But, I think he only wrote 2 papers on which they were officially called. But behind these papers, behind these 2 1963 papers, there were 2 women, one of whom had a career in academia and the other one not. Because of where his programs, they are acknowledged in the papers, okay? But nobody knew who they were until somebody that I know very well, the now professor at MIT, Dan Hoffman, has also involved as a summer school at the Istituto Veneto di Lettere e Scienze d'Arte, participated too, and he was involved in that. So he wrote a paper, and you can find this on Quanta magazine. Okay, it's an amazing paper, and if you write to me, I'll try to send you the reference. So all this stuff was done by one of these 2 women. I forget which one did what. Okay? But what you see here are numbers and then hand-drawn contours, and on top of that, this is the jet stream, and these are the tilted troughs, which I drew in my hand. Okay? But you see quite clearly that this is tilted trough passivation. Okay? That is happening in this system of 14 ODs. So that Bob reproduces certain observed aspects of the atmospheric index cycle. So I have to really tell you what this index cycle is. What it is what Jeremias did in that 1950 paper. He looked at weather maps, and I think maybe monthly means or something like that, between 2 latitudes, and I forget the exact latitudes, but it might have been 30 and 60 degrees north, or maybe 40 to 50, something like that, over the Pacific. And the index is essentially the mean velocity of the zonal flow. And you see that there is a cycle, not a purely periodic cycle, but there is something that is going up and down. So, okay, so it does reproduce that because you can see that here, these isoplines, these streamlines are closer to each other than they are here. And in addition, there's also, so it reproduces the index cycle while the latitudinal displacement, I misspoke myself. It moves up and down, but not really, does not reproduce intensity variations. So the motion up and down is essentially a seasonal component. It also reproduces certain aspects of tilted trough of shape isolation, rotating differentiated into that. So essentially, this very relatively simple numerical work reproduces these 2 features of both the observations and what. Next one, please. Okay, so we're coming back to this highly idealized diagram. So, I forgot who it was who on Monday asked the question, why doesn't the Hadley cell nerve extend to the poles like on Venus? The question was, maybe someone did you ask that? Why does the cell really extend to the poles on Venus or something like that? It does. So, okay, so what you're seeing here is essentially an attempt at placing the different planets on these plots. Okay, so the delta T represents essentially the mid-latitudes, where the difference is between 30 and 60 degrees on average is roughly 10 degrees Kelvin. And this one represents the tropics because the difference, the temperature profile in the tropics is very, very flat. So let's say it's only of order of 1 degree, okay? And in the tropics, both the rotation, you are projecting the rotation of the Earth onto the local verticals. So F, the lowest parameter, is small, and delta T is small as well. So this is a plot, okay, of F and T with latitude. Okay, so you see that what is happening is that F goes from 0 to 1, okay, and this happens to T. Let's go to the next one because it's a cleaner version of this. This is also due to Peter Reed, who had a better graphical iris at his disposal. Again, logarithm of the height number, logarithm of the Taylor number. And what you are seeing here, this is Mars, this is, quasi-periodic review, this is Earth, this is Titan, which essentially looks like the tropics. And Venus, let's see, Venus is somewhere up here. Okay, so the Taylor number is even smaller and the height number is even larger. So this is just based on all the study, first crack at comparative planetology, more precisely a comparison of the atmospheres of the of 3 terrestrial planets and 1 of the satellites of Jupiter, Saturn, about which we have some pretty detailed data. So I think that that's as far as we'll go before the break. Can we just look at the next one? I remind myself, yeah. Problem, read the paper, the report. Okay, so, if you want to do something, try to read the paper and think some more about it. I think we're going to take a break and continue with the rest after the break and discussion. But if you have any questions right now that cannot wait till the end, not we can just follow for the discussion. Yep.
Just maybe something, but I don't understand. What is the time between this transition of the state? State assistance state by the periodic provider, then
let me hold on just a second. Let's go back to the one with the tropic vacillation.
Yeah.
Before.
Which one? Here.
No, this is not time. This is.
No, but at the same time, you will be
in time, well, I mean that the structure of the solution, okay, it's the structure of the solution. There are two things that happen in such a bifurcation. The spatial pattern changes and the behavior in time changes. So that's what I'm talking about. It is not the time that it takes. The time that it takes is a matter that we'll discuss at some time later when I will be talking about non-autonomous and random dynamical systems. In other words, the ones where these assumptions that are time independent do not hold. There, one looks specifically You see here, when you talk about the changing parameters, this change takes an infinite time. You know, it's infinitely slow. Okay. But the next thing, precisely because typically those parameters do change some time scale, okay, in these broader framework of non-autonomous and random environment systems, you can discuss how that might change in time. In other words, how you would go from a Hadley circulation to, let's say, if you took Venus and accelerated its rotation around its axis on some time scale, how would it turn into a circulation that looks more like Earth? Okay? That's a very good point, which we'll try to address. Okay, so 10 minutes. Yes, so the idea is that you have to keep a calm in the face of deterministic chaos and beyond. And let's see, okay. Let's see, the next one might have the subtitle. Is actually, this is actually a cartoon out of the New Yorker. New Yorker magazine. Okay, so next please. Okay, next. So, again, I said much of the motivation in the climate and environmental sciences is actually prediction. Okay, as it is in finance and mathematics. So, okay, this is some quantity which is constant in time, like the radius of the Earth. You have some points, so you only need one number, and the more measurements you get, the better you can estimate and predict it. A little harder periodic phenomena, so things like sunrise and tides, only 3 numbers, period, amplitude, phase. And multi-periodic phenomenon, that's called technical quasi-periodic, or beyond that, almost periodic, it's an infinite number of periods. So, for instance, celestial mechanics, you still need finitely many numbers, number of periods. Then finally, aperiodic phenomena, thermal convection, weather, infinite phenomena. So, clearly, the more complex the phenomenon, the harder it is to predict. And, essentially, that's why you need the dynamic persistence theory. Next, please. Okay, so having talked, actually, I refer to them as A and B because they were published in the same journal of atmospheric sciences, the convection one first, and the one that was called Mechanics of Oscillation later in that year. Okay, you've all seen this, and if you haven't, it's very easy to go on the web, Wikipedia, and other sources to see this sort of thing. This is essentially an attempt to talk about the statistics of this kind of deterministic chaos, so phenomenon with sensitive dependence on initial conditions. Again, it's actually very interesting because, you know, that Henri Poincaré, aside from being the great mathematician that he was also a physicist. He actually was nominated over 50 times for the Nobel Prize in Physics. He contributed to what's now called first or limited theory of relativity, and a philosopher of science. And he wrote a book which is called Science and Method. This translated in English, Science and Method. And chapter 4 is called Le Hasard, chance. So in that chapter, very specifically, he Of course, he became aware of this problem by working on celestial mechanics, but beyond that, he speaks specifically of sensitive dependence on initial conditions. He uses that sentence in leading to chaos. You know, there's nothing, leading to stochastic processes. There's nothing really random about flipping the coin or throwing a die. It obeys Newton's laws. Okay? So it is only the fact that the result is not an obvious connection to the initial conditions. And he specifically mentions as his second example of such hazard, arising from deterministic laws, the weather. Okay? So I mentioned to you that there are many meteorologists who think that really Edward Lorenzi discovered deterministic chaos. It was Poincaré and Lamar, and after that there was a lot of work on the forced van der Pol equation by John Littlewood and Mary Cartwright and other things, but clearly, Ed Lorenzi's example is amazing. So this is about applying the sorts of measures that one applies to stochastic processes to this particular model. Okay, so this is just one piece of an orbit out of this paper. Okay, and these are also taken from the paper. And what is indicated here is what's called, in meteorology, empirical orthogonal functions. These are the eigenvectors of the covariance matrix. In fluid dynamics, they are called POD, principal orthogonal decomposition, and they're called all sorts of things in other fields. But essentially, we're just talking about linear algebra of covariance matrices. So, this is the leading one. Okay, so a covariance matrix is symmetric, so it has real eigenvalues, and also happens to, in most cases, to have distinct eigenvectors and no multiplicity, but that's not necessary. So, in any case, this is the first eigenfunction, which points to the two wings of the butterfly. This is the second eigenfunction along the axis of symmetry. And the third one necessarily is perpendicular to the first two, symmetric matrix, and so it just points in this direction, which is less interesting. Okay? It's a plot of y. Okay, so there are x and y are in these directions, these here, this direction. Plot of that plus projection to the y, z, and xy planes, and then for the canonical chaotic values, this is a suitably normalized Rayleigh number, which indicates it's a non-dimensional measure of the temperature difference between the two plates, between the two motion occurs, the lower one being heated, the upper one being cooled. This is the Prandtl number, and this is a non-dimensional wave number for which this thing was obtained by Lorentz in that time. Next one, please. Okay, so there was an earlier problem, just get the trajectories. This one is, again, you can find software to compute the statistics of the Lorentz butterfly, probability distribution function, EOFs, and do so. Okay. Again, if you want to feel that you haven't wasted your time listening to me, do something. Okay. Next. Okay, waves versus particles. Next. Okay, so what we are talking about here is what's called in statistical physics coarse graining. We look at the Markov chain description of low frequency variability. So you want to first reduce the number of degrees of freedom to the most important ones. You want to associate it with the highest variance. So I don't know whether, how many of you have had a course on probability? How about statistics? So you know that for covariance matrices, the eigenvalues are something equal to the variance associated with that particular direction. So you are looking at some distribution. So K is the order of the eigenvalue function. Let's say this is sigma K. So you're looking at some sort of distribution like that, where sometimes in English it's called the Scree diagram. Scree is the small stones, you know, result from the erosion of mountains. So yeah, and let's say that you stop somewhere here, okay, and then you try to yeah, that's something that I forgot about, the hybrid mode, so that you can't really use the backbone.
When we reset everything, we forgot to choose the camera.
Okay.
Now we have.
Okay. So first, you reduce the number of degrees of freedom to the most important ones, highest variance, and then you describe the dynamics in this reduced subspace. So I mentioned already, these are clearly two different types of flow, zonal and blocked, tau Z, sorry, in American English, Z is Z. I forget sometimes when I'm on the continent, say Z. So this is, say, the typical duration of the persistence in such a regime. So you see here you have a diagram of the number of events versus the duration. And this is the number that's up here. Okay, and there are some other kinds of regimes like that, maybe not quite as important, but they're not really the only ones. And some of them ones for weight training. And the interesting thing is actually that the time mean, if you look at the time mean of the flow, it's not here and not here and not there. If really the mean has no particular dynamical mean, one should not confuse the time mean with the most, with the root of the bifurcation. Okay? It happens to lie somewhere between the branches of the bifurcation tree, but it's not necessarily exactly the same. No particular, you have to understand that because of this success of bifurcation of Bragg instability being a huge step towards explaining mid-latitude storms, for decades, dynamic meteorology dealt with linearized models of flow. And, the time mean is not a fixed point of the equations. Okay? So this is something that I have a lot of trouble with many of my colleagues in the field of dynamic meteorology. Okay? So this is essentially the Markov chain description of low frequency variability. So that's sort of the particles in that analogy. Next one, please. So, this is a sport. Classifying regimes, identifying regimes, describing them. There are lots of papers on that. So this is based on a paper that we wrote in the Proceedings of the National Academy of Sciences in 2002. It was in connection with a symposium, so-called state-of-the-art symposium of the Academy. In the year 2000, we've all been trying to imitate to some extent what Hilbert did at the famous International Congress of Mathematicians in Paris in 1900, and talking about what we'll do in the next century. So this is was a special issue of the PNAS that dealt with the symposium. So classification schemes by position, cluster analysis, so again, this is applied statistics. So, people took different data sets. NH stands for Northern Hemisphere. And this is fuzzy clustering. And this one was both for the entire Northern Hemisphere and sectorial. I mentioned Pacific North American, North Atlantic, Eurasian sector. Hard clustering means, hierarchical clustering, which is enormous, big and PDF estimation. There was incidentally, at about that time, an entire school of studying this problem, which was referred as the Italian school, because basically Roberto Benzi and Alfonso Sotera, RIP, and actually it turns out that this Hansen had actually Italian ancestry, so he could also belong to the Italian school, involved also Malguzzi and Speranza and so on. So they were probably the first ones to look at PDF estimation, univariate. They basically tried to classify everything in terms of a zonal wave number, and multivariate, etc. So let's say there was a lot of work on this. Next one. We'll continue now by persistence. Okay, looking at pattern correlations, Northern Hemisphere, Southern Hemisphere, minimum of tendencies, another thing by which you can categorize these things, trying to determine when the flow is in a persistently anomalous situation is by looking at the minimum of the velocity in phase space. Velocity in phase space, again, in dynamic meteorology, is called tendency. At the time when people were trying to do forecasts, essentially manually, looking at maps, and the difference between two maps was a tendency. Okay, so this was done in a model that was the PhD, essentially out of the PhD thesis of Amal Graf. This Japanese meteorologist, this then the first PhD student of Bernardo Grau with Roberto Tar. So they kept doing this, and okay, and then people started looking really at the transition probability. So that we can go back to the previous diagram. Okay. So trying to determine essentially these probabilities of transition from zonal flow to block flow, and back, etc. So you must know that to this day, with these huge things at the European Center and other big national or international so-called operational weather prediction centers have, you are doing pretty well with predicting the persistence of the flow in a block regime. But you're not doing that well with predicting the moment when the transition to a zonal flow or the other way occurs. So having, a degree of effort which is, millions of times higher than just the simple models that were being done in the 60s, 70s, and 80s, has not necessarily solved this problem. We are doing pretty well with persistence. I mean, I look at my, cell phone, and I have a particular, these days there are various private companies, in particular in the United States, but not only, that will predict for you the weather in any city in the world. When I travel, I look at this and it says Pisa is going to be this hot through the end of my stay next week. And that is quite likely to be true unless there is such a transition. Okay? So, you know, it's interesting because one of the papers that Ed Lorenz wrote in the 80s had to do with, at that time, the question was whether statistical methods can beat dynamical ones, in other words, methods based on discretization of the governing equations of motion or not, for weather prediction. Well, you know, for weather prediction, it's quite clear by now that dynamical methods have won. But if you look beyond the season, that is not necessarily so. The last time that a comparison was done between so-called intra-seasonal, in other words, in this interval, you know, in 10 and 100 days, and beyond, in particular forecasting the El Nino Southern Oscillation, there's still about a dozen stochastic models and 24 big models. And our model, which is based on some, let's say that was my UCLA research group, the theoretical climate dynamics group, I won't have the time to talk about it, to get to that point. Whereas rated as being highest amongst the statistical models and competitive with some of the biggest models. So beyond a season, we are still at the point at which we were for numerical weather prediction 3 decades ago. Okay? So this thing, you know, makes sense. Okay, let's go back to where we were before. Okay, so transition probabilities. And again, I won't have the time to go into further details. Let's just go to the next slide at this point. Okay, so this is, again, out of essentially these papers published out of the PhD thesis of Masaki Moto, 4 regimes, okay? In some sense, in any statistical analysis, there's a trade-off between the amount of detail and the amount of confidence. Now, if you have too many particles, you have lesser confidence. If you have a smaller number of particles, regimes have greater confidence. So, you know, this is sort of the minimal representation of such a Markov chain. So I have 4 regimes, essentially block versus zonal, in the Pacific North America, PNA, and the Atlantic European sector, respectively. So this is, again, remember that this is where Florida is. This is Yucatan. Okay, we are over here. Okay, Greenwich is for example like this. So this is you know, you have a large negative anomaly. So you know, go like that over the North Pacific. And some other features that characterize this regime. This is the opposite regime in which the anomaly, so again, in meteorology and climate, an anomaly is not necessarily something bad, like in medicine, okay? An anomaly is just a difference between a particular map and the average map. So it can be a daily map, or it can be a monthly map, or whatever, okay? Sorry, I forgot when I talked about consistent anomalies. So you see the largest one here, this is a low, this is a high here, okay? And typically you have some other features which, for instance, you see here over Florida, there's the ones which are shaded as statistically significant. And then this is what's happening over the Atlantic. So this is zonal North Atlantic Oscillation. Okay, basically, the North Atlantic Oscillation is the seesaw between the Azores high and the Icelandic low. So when the flow is zonal, that means it's like this, and the jet has a high speed, And the blocked one, it's the seesaw is, this is like this, and in this case it's like that. Okay, so you have an anomalous low here and an anomalous high. Okay, so you have something like this omega block that I showed you before. So basically, this is sort of a minimal representation of the particles in the phase space of the large-scale flow. Next one, please. So again, the lowest common denominators are where this is a comparison between two sets of, okay, on, let's go back to the ones which have the list of the different clustering methods. One more. Here. So the comparison will be between this paper, okay, and these two papers, and the comparison was done in this paper. And the point is that Mike Wallace, who is a dominant figure in observational meteorology, kindly agreed to have his paper, which was already a little bit before our work, published in the same issue of the Journal of Atmospheric Sciences. And then this paper made a comparison between the two. So let's go now to the slide where we were, with the three plots on top of each other. Oh, no, it was the one that we had just before. The next one. Yeah. So you see, this is a Chang-Wallace classification, and this is the one that we did in this paper, Smith, Gill, and Ide, okay? And it basically shows that by taking slightly different data sets and very different methods, we wound up with a subset of 3 out of the 4 things that I showed you. So it's really, for whatever it's worth, this is certainly not a mathematical proof, but it is an argument of plausibility that you look at the same phenomenon, you look slightly different observational data sets in terms of resolution and duration and so on, and very different applied statistical methods, and we will sort of get the same stuff. Well, you can go home and have a drink. Okay? You're not finished, but you've done pretty well. Okay? So you can put with your but it says that essentially this dynamical system has a certain kind of course gradient. Next one, please. Okay, so again, this is another one of these maps. I told you already, these are 500 millibar, 500 hectopascal map for this month of January '63, when Ohio and some other people from the US Midwest froze their asses off. You see flow is coming down from Canada and making it very, very cold. And so now we're going to go on to some modeling. Okay, so these were observational papers that noticed the recurrence and persistence of blocking. And actually, Drew Charney, whom I first met in New York at NASA's Goddard Institute for Space Studies, and later when the meteorology group from there moved to another bigger NASA center close to Washington, D.C. there. I remember over lunch at the Goddard Space Flight Center, Jules said, there's been a lot of courtship about this blocking, so finally there had to be a course. So, he was a fun guy. And actually, the paper that he did, that I'll show you in a moment, was done during the sabbatical he took from MIT that he spent at UCLA before I got there, but he did it with a student of Andrea Fatala, And you'll see this in a moment, but just to show you again, this blocking ridge, which is just upstream of the Rocky Mountains. Okay, that's going to be the key point. Not going to talk about this omega block west of you. Next one, please. So again, I showed you this one. Let's go. Next one, please. You've seen this one before. So this is sort of the result. Again, it is not, this picture is from the Trinity War paper. Okay? Simple conceptual models, that's the word about toy models. Simple conceptual models are sometimes treated with disdain by people who do big models. So they call them toy models. But Einstein said, if you want to be a good scientist, you should keep your childlike wonder about the world. So toys are good, okay? They give you ideas. They're not the end of the story, but they're a very good beginning. So basically, again, the bifurcation diagram is not in the paper. In the paper, Charney talked about orographic resonance. Now, this is a rather peculiar concept of resonance because this is a stationary pattern. So it's sort of a zero frequency resonance. You can call it that, or you can show that it's really, you have a bifurcation. So what is here in the bifurcation diagram? The model has three ordinary differential equations. There's one zonal component, so that is just flow from west to east, plus one wave, so that's the sine and the cosine, that makes a total of 3 ODEs. Okay, so what is plotted here is the coefficient of the zonal wave in the forcing. So what does it correspond to? I showed you on Monday that there is a mean slope of the tropopause from higher at the equator to lower at the pole. Here again, because the air here is hotter and colder over there. And this corresponds by a geostrophy with something that drives a flow from west to east. So the intensity of that flow that is imposed by the fact that the atmosphere is an open system, this is the size of A star for forcing. And what is plotted here is the intensity of the zonal flow in the solution. Okay? So the diagonal just says the flow does exactly what it is told to do by forcing, and the deviation from that, the bifurcation diagram, is what the flow really does. So you see that the flow will be zonal at very high forcing, and it will also be zonal at very low forcing. But in between here, there are three possible solutions. So that's what's sometimes called bistability. Okay, so there are two stationary points, both of which are stable. One is zonal, the other one is more wavy. So it's these two pictures. What is shown here is the topography. Again, this should be ocean and land in quotation marks. So it's a wave number 2 topography, which corresponds essentially to the existence of 2 continents and 2 oceans. And you see the wave is aligned with a positive topography. So zonal, the zonal flow is not purely zonal, like this one is, but it's only weakly wavy, and the ridge of the wave is aligned with positive topography, and the trough of the wave is aligned with negative topography. Okay? So this is the zonal solution here, and the blocked solution here is this. So first of all, the amplitude of the wave is much bigger, and then it is in anti-phase with the topography. The trough of the wave is over land, and the ridge is over the ocean. So this ridge essentially corresponds, so let's go back to the one where we have a map, okay, corresponds to this. Okay? In this highly simplified picture. So now, as I said, Heine actually talked about the orographic resonance, but, you know, orography, I mean, somebody who is a geoscientist who goes beyond fluid envelopes also to the solid earth, you know, orographic instability sounds like something that would, you know, form the Alps. So I don't like orographic resonance, I say topographic resonance, but anyhow, okay? Topographic leads to multiple equilibria zone gets blocked. It was much criticized by all these people who are only doing linear dynamics as being unrealistic because it requires the forces to be too strong compared to the one that is given by this difference in altitude of the tropicals. Okay? Next, please. Now, as I said, we're not quite done, even with the most detailed models, with reproducing this. In particular, we don't know exactly how to predict the onset or blocking or the disappearing. But somewhere in between very simple models and very complicated models and reality, there are laboratory experiments. So this is out of that Weeks et al. Paper in Science with the baotropically forced rotating annulus in Harry Sweeney's lab in Austin, Texas. So the annulus, as I said, is fed fluid from the bottom, so it goes up this way and down that way, and then it's has a machine topography. Now, it's actually interesting. The story was that a student of mine, Rudolf Tian, wanted to do an experiment. We used to have at UCLA, before I got to Fritz Busse, one of the great dominant figures of experimental work on convection, real convection. But after he left, there wasn't anything like that. So you don't want to do something. Harry and I had met. He was interested. I sent you them over. They did a simple experiment in which they just put some very simple topography, a bunch of soil cemented in a certain way, and they did realize that there were differences in the flow with and without this very crude topography. So Harry got very smooth and nice topography and a strong pump. And so what you see here is in the annulus, the zonal versus blocked flow. Okay, so here you have more pronounced radius versus what you have here. And this is a probe in the fluid that gives you this velocity. So you see that there is high velocity, which is smooth, and low velocity, which is very irregular. And if you look at the relative duration, percent of time blocked, as you increase the Rossby number, in other words, pumping, basically, you see that you have here, it's blocked all the time, okay? And here it's zonal all the time, and then the straight line between the two, which corresponds very much to this paper, which had not three components in a so-called beta channel and a straight channel, which corresponds roughly to 30 to 60 degrees latitude of the Earth, but 25 spherical harmonics on the sphere with certain simplifications. And the experiment says what that model is. So maybe there is something that indeed connects at least the West Coast ridge of blocking with relatively simple, easily understandable dynamics. Next. Okay, oscillatory modes and broad spectral peaks. Well, we're going to see some statistics for broad spectral peaks and so on in lecture 5. But let's look at oscillatory modes right now. Next, please. Okay, so, you know, multiple waves versus particles, which one is it and how does it help? Next. So again, the title of this paper in the PNAS was Weights versus Particles with quotation marks, a pathway to prediction question. Is predicting as harder to claim to be? Well, here are some of the alternative explanations. Okay, this is pictures of phase space. Let's say this is zonal and this is blocked, or this is the three kinds of regimes which we found in this without paper, PNA, reverse PNA, and blocked NAO. Okay, so either regimes but slow phases of oscillations, high oscillations but instabilities of particular equilibria. In this paper, we found that essentially there were two kinds of zonal flow that had a certain kind of sharing of instability, but there was hot bifurcation from the block regime later. And then how about chaotic itinerancy? So Masakimoto, with a postdoc of mine, Epo published a paper in which they talked about this chaotic itinerance. So how about Meaner, null hypothesis? Well, this was a proponent, very prominent proponent of the linear school, which said all of this, all of this is nonsense. Linear is enough for just some random superposition of mutually stable oscillators. Some phase here with two waves just align and so on. And finally, it's all due to red noise. So this is 76 as a line. So, this is not resolved. So, there's room for people to work on this. You might even find that some of these models are interesting enough to actually prove that the results are necessarily, rigorous. Okay, but we don't know. Next. So, is predicting as hard as it is claimed to be? No, it's actually quite easy. Just flip a coin or roll a die. What's difficult though is just trusting the prediction. So no amount of testing statistical hypotheses will really settle these things. Now, what it does is dynamical understanding. Next. Okay, that's where a little understanding of what we're trying to predict helps. So I think that it's lovely that we have an ergodic theory of deterministic dynamical systems, but the question is which dynamical system? Okay. I think we're pretty much done. Sorry, this is what I wanted to highlight has gotten erased. You can see this form. So these are some of the various references, mathematical and dynamical, but you'll have to look up some of those to see which ones. To the best of my recollection, it is that Bill Robertson paper in PNAS, and that's one of them. Yes, that's this one, and the other one is the recent review paper. There's a book that came out a year or two ago on the issue of what is now called S2S prediction, sub-seasonal to seasonal prediction. So I told you the frontier lies, which was edited by Andy Robertson, who was the co-author of this paper, and Frédéric Guittard from the European Center. And we have a chapter in there that updates the paper for 20 years ago. Okay? Those are the best ones to read. I'm sorry about this little accident. I think that this is the end. So we still have time for questions and discussion. When we look at the next one, I think it just says reserve slides. Let me just say that for those who might be interested in the more mathematical aspects of this, there is some work on the partial differential equations that are being used in physical fluid dynamics, various isotrophic and other such systems. And in general, this is not what the course is about, but there are entire books about bifurcations and limits on the size of strange attractors and the partial differential equations of fluid flows. And I didn't include them in here because I didn't think that this was the audience that was most interested in those things. But you shouldn't believe, like many methodologists, that this only applies to lower order systems. There's a well-developed literature, number of people. Roger Tenam and Peter Constantine, and quite a few other people have done a lot of work on these kinds of problems for systems of non-linear partial differential equations. In particular, degenerate parabolic, off the type, and these sorts of problems. Or isotrophic, etc.
We start again this afternoon. Next lecture.
Oh yeah, we start again at 3 p.m. So if you want to leave a little earlier today, at 3, okay?
Today is a special day. There are 2 lectures.
Yeah. This is only going to happen this one time. And then from the 4th lecture on Friday, and 5th and 6th on Monday and Wednesday next week. But I think it's going to get more interesting as we go into non-autonomous stuff, which is really about how you deal with a system which is already pretty complicated, even for constant forcing, and you start doing anthropogenic changes in composition of the atmosphere and some other. So I think that from the point of dynamic systems, it only gets more interesting. And there will be more mathematics. But it's not the kind of purely Blackboard mathematics